When we first began studying motion, we talked about kinematics, and we described motion in terms of how far something could go, how fast it would go, if its velocity was changing, how much time it would take, those types of things. And we had three main kinematic equations that we used very much. And so we're going to begin talking about rotational motion and dealing with a rotating frame of reference. And we're going to still describe how far does something go, how fast is it going, is that velocity changing, but all from a rotating perspective, from a rotational frame of reference. So we get into rotational kinematics, and we begin to introduce some new variables to us that describe kind of the same things we've been talking about, speed, velocity, acceleration, but when it comes to a rotating reference frame. So let's get started. So remember that position of an object was represented by an X, and this could have been represented also by a Y, but we had a coordinate plane, we had a location of something, we had a frame of reference, and we described position or change in position using meters. But when we talk about rotational motion, so that linear motion is sometimes called translational motion. But in rotational motion, position is going to be represented by the angle that you're dealing with, theta, which is familiar to us. But it's going to be represented by that angle theta and the radius r. So theta is going to be measured in radians. Remember, a radian's not necessarily a unit, but it's a relationship between the circumference along a circle and the radius of that circle. And when you get like the radius equal to the circumference in terms of distance, now you have one wedge of a circle that looks like a wedge of a piece of pizza. That is 1 radian. If you go all the way around the circle, you get 6.28 radians, or we say 2 pi radians. So we have a frame of reference to start at. Linearly, you would have an origin, and moving to the right was positive and moving to the left was negative. From a rotational perspective, we still have an origin, but our direction is going to start at the positive x-axis, which is out here to your right, and we're going to rotate counterclockwise. Remember, this would be at 0 degrees, and then 90 degrees, 180, and all around. So we're going to rotate counterclockwise. That's going to be considered a positive rotation. Now, if our position changes, we call that displacement. In translational motion, we would say displacement was a delta x, final position minus original position. And so if I started at a position of 3 and ended up at a position of -1, I would say my displacement would be -1 minus 3, which is a -4. Angular displacement or rotational displacement, sometimes because we're moving through angles, we also refer to this as angular displacement. Angular displacement would be delta theta, change in theta. That is not a vector, but for small changes, it does behave like a vector. We will use our right hand to tell us the direction that this object went. So we use what's called the right hand rule, which we kind of spoke about a little bit earlier. But with the right hand rule as it relates to displacements, we simply are going to essentially run your finger along the radius. So start at the origin, move your finger along the radius, and then the palm of your hand is going to go in the direction of that change. So if my change went this direction, my palm wants to face that way, my fingers would curl in that direction. And so I'm rotating in a counterclockwise direction, and then my thumb would be pointing outward of the screen, and that's an important part about using the right hand rule. So when something is moving, certainly we have a displacement, and we can see that if you have something rotating through an angle, you change your angular displacement, but you also can cover kind of a linear distance along the x. axis or along that arc. And so we would refer to that as a linear distance, but because we're going in a circle, it's kind of an arc distance, and that's referred to as S. It would still be meters. We could also include that and relate that to X, but a particle that's going to rotate through an angle, delta theta, also translates through a distance S, which is the length of the arc that would define that path. The distance S is related to that angular displacement, change in theta, by the equation S equals R times theta. S equals R times theta. So where S is a linear motion, theta is an angular motion, so to get from a linear measurement to an angular measurement, and this is just looking at position-wise, we need the radius. If I traveled all the way around the circle, then that S would be the circumference of the circle. Well, that's going to be radius R times one complete rotation is 2 pi. And so we could say S is R times 2 pi. Well, we know that S to be a special distance that we call the circumference C. And this is where we get this equation, circumference of a circle is the radius times 2 pi, or 2 pi R. So we're moving between linear and angular measurements. So for position, which is X measured in meters, or S, the distance along the arc, and the angular analogy of that is theta. Theta is measured in radians, and to get from X to theta, I need the radius. So I say X is R times theta, or S is R times theta. This just converts from one linear measurement to an angular measurement. Certainly I could go backwards as well. So we talked about position, and then when position changes, we could also look at how quickly that happens, and that brings us to talking about speed or velocity. So remember that if something is going in a circle, its instantaneous velocity would be that tangent to the circle, and it would have sort of a distance over time type measurement. We could say it's change in S over change in T, or change in X over change in T gives us that velocity, right? The same particle that's doing this is going to rotate with what we call angular velocity. Angular velocity is a new variable. Instead of a V, it looks sort of like a W. It's a lowercase Greek letter omega. So all variables for rotational motion are Greek variables. So we have theta, which is our angle. Now we have omega, W. Omega is change in theta per second. So the direction that something is rotating is found by the right-hand rule. Once again, run your fingers along the radius from the axis, from the origin out to the radius, curl in the direction of the motion, and then your thumb would give you the direction of that vector. So this motion is in a counterclockwise direction. This tangential speed, V, and this angular speed, omega, is given by the equation V equals R times omega. Similar process, right? My linear velocity is the radius times the angular velocity. V equals R times omega. Omega is going to be measured in radians per second, just like theta is measured in radians. So omega is how far did you go and how much time did it take as you rotated in a circle. You might have heard of another unit for omega, because we're talking about rotational motion per second. You might have heard of another unit called rotations per minute. That might be something that is also familiar to you. But that is a unit of angular velocity. And then finally, that last measurement is, well, what if this velocity, what if the spin rate here is changing? Well, then we have acceleration. So remember, linear acceleration or tangential acceleration is change in velocity over time. This acceleration would be parallel to or anti-parallel to the velocity. So if your acceleration and your velocity are parallel, then the object should speed up. If your velocity and your acceleration are anti-parallel, then the object should slow down. And we find that the same is true for an object that is spinning. Angular acceleration is given by the Greek letter alpha. Alpha is change in omega per second. An angular acceleration can be parallel to or anti-parallel to angular velocity. The same results are going to happen. Let's say that we take a wheel and we have a particle here, and if we give that wheel a spin, we can see that that particle covers a certain linear distance and it rotates through a certain angle. Certainly if we go all the way around, then we know that that linear distance is the circumference, and that rotational change in theta would be 2 pi radians. Well, if we spun it with a certain speed, then it has a certain angular velocity or a certain spin rate. Well, if we wanted this to speed up, then we would need to accelerate it. If we accelerate it in the same direction as the velocity, then it increases and it gets faster. If we accelerate it against the velocity, then it slows down. And this should kind of make sense to us. Okay. So to get from tangential acceleration to angular acceleration, once again, we just need simply the radius. We say linear acceleration A is the radius times alpha. And alpha is change in omega per second. Just like acceleration is change in velocity per second. Meters per second, if this is linear or translational. If we're dealing with something going in a circle, this is going to be radians per second, or radians per second squared. Now, these 3 units, theta, omega, alpha, there's something that you're going to have to take some time, be very intentional about, and memorize which variable represents which measurement. That's going to be really, really important to your success, and that's just going to come with practice, just like it took us a while to learn the 3 kinematic equations that we had on our equation sheet. You know, we had the V equals V naught plus AT, and we have the long x equation, x equals x naught plus V naught t plus 1/2 AT squared, and we learned when do I use that and when do I not. And then if I didn't have time, I had the V squared equation. Like, having all of those is great for linear motion. Well, we have equivalent equations for rotational motion. But if you don't memorize and get familiar with which variable represents which measurement, then you're going to have a hard time putting those proper measurements in the right place. So this just takes some practice, and we want to make sure that we do practice and go through this. Okay, so let's take a look at kind of an example problem here. Wait, I'm already finished with this one. See if you can see this a little bit better. So don't forget also that when something is accelerating, we can have centripetal acceleration. That's another piece of the puzzle. So let's consider an object that's spinning, and it says, assume the particle is speeding up. So we have an object that seems to be rotating in a counterclockwise direction, which we have said this is positive, right? So we have an object that if we have it, we start, it's spinning, and it's going to speed up. So we need it to go faster and faster and faster. And we want to ask some questions about that spinning object. So it says, what is the direction of the instantaneous velocity? At that point, you're rotating here clockwise. At that very point, if this was a string and it broke, which way would this go? Would it go to the right or to the left, or would it fly out this way? Like, which direction would it go? So we say, what is the direction of the instantaneous velocity? You should note that that direction is to the left. Now, what is the direction of the angular velocity, omega? Which way is this rotating? So our directions are only counterclockwise or clockwise. Well, at that one point, you should see that it's rotating counterclockwise, CCW. Now, what is the direction of the tangential acceleration? Okay, tangential acceleration is linear acceleration. So remember, this thing is speeding up. So which direction is the acceleration? Well, it would also be to the left, because if it's parallel, it should get faster. What is the direction of the angular acceleration? So alpha, what's our change in our spin rate? Remember, well, our object is rotating counterclockwise and we're getting faster, so these should be going parallel to each other, so that should be also counterclockwise. What is the direction of the centripetal acceleration? What direction does centripetal acceleration go? Well, that's always what? At this point, it's going to be toward the center, right? And then what is the direction of the overall acceleration, A, of the particle? Okay, well, we've got an acceleration that's going counterclockwise and to the left and toward the center. So if you add these vectors together, can you see that this should go, if it's going to the left and it's going in, then it should be kind of down and to the left. That should sort of feel right. Okay, so what changes if this particle is slowing down? So let's say that it's spinning, right? Assume the particle is spinning counterclockwise, but now it's slowing down. So what is the direction of the instantaneous velocity? So which way is it going right here? Well, it's still going to the left. Okay, what is the direction of the angular velocity? So it's spinning still this direction, right? But it's slowing down. So shouldn't that still be counterclockwise? Yes. What is the direction of the tangential acceleration? So if this particle is moving to the left, but it's slowing down, to slow down, something's got to be acting against it. So that should be to the right. And then what is the direction of the angular acceleration? So this thing is spinning counterclockwise, but it's slowing down, so something should be working against it. So the acceleration, the angular acceleration, should be clockwise, rotating against it. What's the direction of the centripetal acceleration? Still, once again, toward the center. And then what is the direction of the overall acceleration, A? So I have a linear acceleration to the right, centripetal acceleration toward the center. My overall acceleration should be down and to the right. Hopefully you could take some time and kind of process that, so that should make sense to us. Now that we have an understanding about what these three variables represent, let's get into the equations that we'll use to help us describe and solve problems about the motion of objects as they spin. So frequently we'll talk about bicycles or turntables or anything rotating in a circle, and we're using that term angular for circular or rotational, and we're using the term translational for linear stuff. And so let's do some practice here. So our first kinematic equation started off with describing velocity of something and like how fast something is going, and we had this equation that says final velocity equals original velocity plus acceleration times time. That was how this went from a linear form. If we want to convert this equation to a rotational motion, so instead of talking about velocity, we want to substitute angular velocity. So instead of v, we want to substitute omega. And we want to substitute angular acceleration, alpha, for a, and then time is time. And so we get omega equals omega naught plus alpha times t. So our linear form in a rotational motion, this becomes our first equation. How did we do that? Well, we said, okay, well, if v is v naught plus at, and to get from v to omega, I need to multiply by the radius. V is r times omega. So here we did r times omega naught, and r times acceleration, r alpha is acceleration, and then times time. And now you've got r in every single variable, so we can factor that out, and you get omega equals omega naught plus alpha times t. Okay? So when would you use this? You would use this equation when you have a particle that's spinning and the spin rate is changing. Right? Now there's nothing in here that tells me how far did it go. So I would need a different equation for that. But if I want to know how fast something is going, or if the acceleration is changing, or how long it takes for something to change its velocity, this is the equation I would want to use. Our second kinematic equation we use a lot, and we use this for articles that were at rest. We use this for finding the distance that something could travel. The only thing this equation could not tell us is how fast will it be going in the end. Like, we don't have a final velocity in this equation, but we could use this if we had constant speed, or we could use this if we were accelerating. So let's convert this to the rotational version. We're going to substitute the angle for x. So instead of x, we're going to have theta. We're going to substitute angular velocity, omega, for v. And we're going to substitute angular acceleration, alpha, for a. And this equation now looks like this. Theta, how far something goes, is equal to theta naught, where did it start, plus omega naught times t, my starting angular velocity times time, plus 1/2 alpha times t squared. Okay, so when would you use this equation? You would use this if you were trying to figure out through how many rotations did something go, or through how many radians did something travel in a certain amount of time if the velocity was changing. You could also do this even if the velocity was not changing. If my acceleration was 0, then this would be sort of a constant velocity equation, and I could still figure out how far, through how many rotations or how many radians did something go. Please understand, one rotation and one radian are different, but they're both dealing with kind of sweeping through the angles, right? One rotation, one full rotation, is 2 pi radians, or 6.28. We won't actually use the pi button. We'll use 6.28. Okay, our third kinematic equation was a special case when we took the first two equations and substituted time out, because frequently we're not given time. And so we referred to this equation as a v-squared equation. So you've known this to be my final velocity squared equals my original velocity squared plus 2 times alpha times my change in position. I was given distance, acceleration, starting velocity, ending velocity, no time. So let's convert this to the angular version of this. So we want to substitute the angle for position. So for x, we want to substitute theta. We would like to substitute angular velocity for velocity. So for v, we want to put omega. And we want to substitute angular acceleration, alpha, for a. And so we get this equation, omega squared equals omega naught squared plus 2 times alpha times change in theta. So once again, if I was trying to figure out how far something went, if it was accelerating, or if I knew something was accelerating and I knew where it started and I want to figure out what the final velocity was, I could use this equation. The only thing I can't use here is I don't have time. So let's take a look at one example problem here. So this says the Beatles' White Album is spinning at a 33 1/3 RPM, rotations per minute, when the power is turned off. So we have a turntable that's spinning, the power goes off, this thing is going to slow down. If it takes half a minute for the album's rotation to stop, what is the angular acceleration of the phonograph album? So just like having velocities in kilometers per hour and I have to convert them, or having time in minutes or something, I have to convert that, we have to do the same thing for equations like this. We want to identify what do I have and what am I looking for. So I'm looking for the acceleration, alpha. I know that the starting velocity is 33 1/3 rotations per minute. I could show you how to convert rotations to radians, but that conversion factor, just like seconds to hours, is 3,600 seconds over 1 hour. Remember, one rotation is 2 pi radians. So if I have 33.3 rotations per minute, then that's going to be 2 pi times 33 1/3, and then I have certainly understand that there's 60 seconds in a minute, and I need to convert that too. So this comes out to be 3.49 radians per second. I know my final angular velocity is 0, and I know the time was half a minute, so that's 30 seconds. So I need an equation that has both these alpha, or I need alpha, omega, omega naught, and t. The equation I would like to use here is omega equals omega naught plus alpha times t. I want to solve for alpha, so I rearrange this equation. Alpha is change in omega over time, so this will be 0 minus 3.49 radians per second divided by 30 seconds, and we will come up with a negative 0.116 radians per second squared. This is how we're going to be using these equations to help us solve problems. Once again, it's just going to take you some practice to get comfortable with the variables, but the more that you stick your foot in the water and do that, the better it'll get.